Welcome to the deep dive. We're here to cut through the noise and really distill things down to those key nuggets of knowledge for you.
That's the goal.
Today, we're diving deep into something fundamental, the physics that, well, powers pretty much everything, especially that amazing interplay between electricity and magnetism.
Hmm.
Our source material for this is like a really comprehensive study review,
Right.
packed with the core formulas, definitions, how it all connects, kind of like prepping for a big physics exam.
Right, but hopefully more engaging.
Exactly. Our mission here is to pull out the most important bits, the stuff that really highlights the why it matters for you.
And I promise this is not going to be some dry lecture. These ideas, they aren't just abstract.
No way.
They are literally the building blocks of the tech you use every single day. I mean, from the atoms themselves up to, say, complex X-ray machines. We're going to connect those dots.
Get that holistic view.
Precisely.
Okay, so let's unpack this. We have to start right at the beginning.
Matter.
The absolute basics. Anything that has mass occupies space. The usual states.
Yeah.
Solid, liquid, gas.
Yep.
And in physics, when we measure this stuff, we rely on three key units, right? Mass. That's kilograms, kg.
Right.
Length is meters, m, and time. Seconds, s. Seems simple, maybe, but it's the bedrock.
It absolutely is. And the smallest piece of that matter, the bit that still acts like the element it came from, that's the atom.
Right, the atom.
Think of it like this. A central nucleus, packed with positively charged protons. They define the element, its atomic number, Z,
Okay.
and also neutral neutrons adding mass, giving us the mass number A.
Got it.
Then, whizzing around that nucleus in specific energy levels or shells are the negatively charged electrons.
Electrons.
Crucial.
Oh, absolutely. And quick definitions here.
Yeah.
Sometimes atoms have different numbers of neutrons, but the same protons. Those are isotopes.
Isotopes, right.
And if an atom gains or loses an electron, it gets a charge. That makes it an ion.
An ion. And that process is ionization. Exactly. Ionization. Gaining or losing electrons, getting that charge, it's a huge deal, changes how atoms behave, which is key for things like X-rays interacting with us.
Let's focus on those electrons for a second. In their shells, there's a rule, isn't there? The Tuckenana rule.
Ah, yes, the Tuckenana rule. It tells you the maximum number of electrons that can fit in each shell.
So the first shell, K shell, that's 2 electrons.
2, max. The next one out, the L shell, holds 8. Then the M shell holds 18, and so on.
But there's another rule, the octet rule. That sounds important.
Very important for stability. It states that the outermost shell, regardless of its total capacity from 2 in our menino, never holds more than 8 electrons for stability.
8 is the magic number for the outer shell.
Pretty much. And that outermost shell, we call it the valence shell. It's everything when it comes to electrical behavior.
So,
Well, if those valence electrons are loosely held, free to move, like in metals, think copper, aluminum.
that's a conductor.
Exactly. Electricity flows easily. But if those electrons are tightly bound, like in rubber, plastic, glass.
Then they resist the flow. An insulator.
Precisely. Insulators. That difference is fundamental to, well, almost all electrical technology. Why wires work and why you don't get shocked holding the plug.
Makes sense. It all comes down to those outer electrons.
And it's all driven by energy. Energy is basically the capacity to do work. The standard unit is the joule, J.
Potential versus kinetic energy. Stored versus moving.
That's the basic distinction, yeah. Potential is stored energy. Kinetic is energy of motion. But energy comes in loads of forms.
Like mechanical, chemical, heat.
Electrical, which is just moving electrons, as we said. Nuclear energy, electromagnetic energy. It's all interlinked.
And for the really small stuff, atomic level, there's another unit.
Right. We often use the electron volt, or EV. It's much, much smaller than a joule. Really useful when talking about single atoms or particles.
And that famous equation, EMC4 that links energy and matter directly.
It does. It's profound. It tells us matter and energy are fundamentally convertible. Two sides of the same coin.
With c being the speed of light, which is incredibly fast.
Astonishingly fast. 3 times 10 to the 8th meters per second. A universal constant.
And this energy travels as waves, right? The electromagnetic spectrum.
Exactly. The EM spectrum covers the whole range. Radio waves, microwaves, infrared, the visible light we see.
UV, X-rays, gamma rays.
All of it. And a key point, the higher energy parts of that spectrum, like X-rays and gamma rays, have enough energy to cause ionization.
To knock electrons out of atoms.
Yes, which is why they're useful in medicine, but also why we need to be careful with them.
So how does this energy travel? You mentioned waves, but also particles.
Well, yeah, light and other EM radiation have this dual nature. They act like waves sometimes, but also like little packets or bundles of energy called photons.
Photons, okay.
And these photons, or waves, have two key features: wavelength and frequency. Wavelength is the distance between wave peaks.
Like distance between crests on an ocean wave.
Good analogy. And frequency is how many wave cycles pass a point each second. We measure that in hertz.
And they're related somehow.
Inversely related. This is crucial. Longer wavelengths means lower frequency. Shorter wavelength means higher frequency. Think long, slow waves versus short, choppy ones.
Makes sense.
The formula is CH, lambda nu, speed of light equals wavelength times frequency.
And the energy, you mentioned EHV.
Right, that's the particle view.
Yeah.
The energy of a photon is Planck's constant h times its frequency. Higher frequency means higher energy per photon. That's why gamma rays pack such a punch.
Okay, so atoms, energy, photons. Now let's really get into electricity. How do we harness this?
Right, this is where it gets really interesting, translating these concepts into practical power.
It starts with charge, right? The coulomb.
The Coulomb, symbol C, that's the basic unit of electric charge. And get this, 1 Coulomb is a huge number of electrons.
How many?
About 6.24 times 10 to the 18th electrons, just mind-bogglingly large number in 1 unit of charge.
Wow. So charge is the stuff. How do we measure its flow?
That's amperage, often called amps or symbol I. It's the rate of flow. How many coulombs pass a point per second?
Like gallons per minute in a pipe.
Exactly. 1 amp equals 1 coulomb per second. Then you have voltage, symbol V.
That's the push.
That's the push, also called electric potential difference or electromotive force, EMF. It's the force driving the electrons through the conductor.
The pressure in the pipe.
Perfect analogy. 1 volt is defined as 1 joule of energy per coulomb of charge. Energy per charge.
So these charges, how do they behave? Are there rules?
Oh, yes. The laws of electrostatics, 5 main ones. First, the simple one, like charges repel, opposites attract.
Positive repels positive, attracts negative. Got it.
Second, the inverse square law. The force between charges weakens really fast, with distance proportional to 1 over the distance squared.
So double the distance, quarter the force.
Precisely. Third, charge tends to distribute itself over the surface of a conductor.
Okay.
Fourth, charge concentrates at the sharpest curves or points on a conductor surface.
Interesting. Like Leighton rods.
Kind of related, yeah. And fifth, crucially, in solid conductors, it's almost always only the negative charges, the electrons, that actually move. Protons are stuck in the nucleus.
Only electrons flow. Good to know. How does something get charged in the first place? Electrification.
3 main ways. Friction, rubbing things together like a balloon on your hair.
Classic.
Contact, just touching a charged object to an uncharged one, transfers charge. And induction, bringing a charged object near a conductor, can rearrange the charges within it, even without touching.
Induction. Like charging without touching.
Yeah. Once you have mobile charges, an electric current is just those electrons moving in basically the same direction.
Through conductors, like copper or gold.
Right. Or inhibited by insulators like rubber or glass. And then there are semiconductors.
The in-between materials.
Exactly. They can act as conductors or insulators depending on conditions. Super important for electronics.
And there's DC and AC current.
Correct current, DC. Electrons flow one way. Think batteries. Alternating current, AC. Electrons wiggle back and forth. That's what comes out of your wall socket.
Okay, so to make this useful, we need a path, a circuit.
A complete pathway for the electrons to flow. And every basic circuit has 3 essential components interacting.
Let's use that water analogy again. Voltage.
That's the pressure, the push,
Yeah.
potential difference.
Current, amperage.
That's the flow rate, how much charge moves per second.
And resistance, measured in ohms.
That's the opposition to flow, like a narrow pipe or friction.
And the resistance bucket.
The voltage bucket pushes, amperage bucket flows, resistance bucket holds it back.
What affects that resistance?
4 main things. First, the material itself. Conductors have low resistance. Insulators have very high resistance.
Makes sense.
Second, length. Longer wire, more resistance. More chances for electrons to bump into things.
Okay.
Third, cross-sectional area. Thinner wire, higher resistance.
Yeah.
Less room for electrons to flow.
Like a narrower pipe.
Exactly. And fourth, temperature. Usually for most conductors, higher temperature means higher resistance because the atoms vibrate more, getting in the way.
Got it. Material, length, thickness, temperature.
Yep.
And the relationship between voltage, current, and resistance. That's Ohm's law.
Ohm's law, the fundamental equation. V equals IXR. Voltage equals current times resistance.
So they're directly related. More voltage means more current if resistance stays the same.
Absolutely. Increase the push, V. You increase the flow, I, assuming the pipe's resistance, R, doesn't change. It's beautifully simple, but governs so much.
Now, how circuits are actually wired up, series versus parallel?
Two main ways. In a series circuit, everything is connected end to end, one single path.
One loop.
Right. The current I is the same everywhere in that loop, but the voltage, V, gets divided up among the components.
And if one part breaks?
The whole circuit goes dead, like those annoying old Christmas lights. One bulb burns out, the whole string is dark.
Oh, I remember those.
And total resistance in series is easy, just add them up. R total R1 plus R2 plus R3.
Okay, what about parallel?
Parallel circuits have multiple branches, multiple paths for the current to take.
Like lanes on a highway.
Good way to think of it. Here, the voltage, V, is the same across each branch, but the total current I splits up, dividing among the branches.
And the big advantage?
Redundancy. If one component in one branch fails, the other branches keep working. That's how your house is wired.
So my toaster breaking doesn't kill the lights. Thank goodness.
Exactly. Calculating total resistance is a bit trickier, involves reciprocals. 4R total equals 1R1 plus 1R2. But the reliability is key.
Okay, that's a solid overview of electricity, but you said it's linked to magnetism, so what does this all mean for that?
It means everything, really. Magnetism isn't some separate, mysterious force. It arises directly from the movement of electric charges.
Moving electrons create magnetism.
Moving electrons, moving protons. Any moving charge generates a magnetic force field around it. And interestingly, that field is always perpendicular to the direction the charge is moving.
Perpendicular, okay.
And in materials we think of as magnetic, like iron, nickel, cobalt, what's happening at the atomic level is that the electrons are spinning in such a way that their tiny magnetic effects add up. They align.
So it starts at the electron level.
It does. Two main atomic effects. There's orbital magnetic movement. The electron orbiting the nucleus acts like a tiny loop of current, creating a magnetic field.
Like a mini electromagnet.
Sort of. And then there's spin magnetic movement.
Mm-hmm.
The electron itself, spinning on its axis, also creates a magnetic effect. It's an intrinsic property.
So tiny magnets at the atomic level.
Exactly. And in magnetic materials, clusters of atoms align their magnetic moments in the same direction. These clusters are called magnetic dipoles or magnetic domains. They act like tiny bar magnets.
And together they create the overall magnet.
Right. They create the larger magnetic field we can observe. We draw this field using lines of force or lines of flux.
Invisible lines.
Invisible, yes. They flow out of the North Pole, loop around, and go into the South Pole outside the magnet. And importantly, they flow south to north inside the magnet to form continuous loops.
Continuous, never crossing.
Never crossing. It's a 3D field. And how close together those lines are, that's the magnetic flux density. It tells you how strong the field is.
Are there units for magnetism like volts and amps for electricity?
Yes. The SI unit for the total magnetic flux is the Weber, WV. 1 Weber is 10 to the 8th lines of flux. A lot of lines.
Okay. And for the strength, the density?
That's the Tesla, T, or sometimes the gas, G. You'll see both. The conversion is 1 Tesla equals 10,000 Gauss. Tesla is the main SI unit.
Got it. Weber for total flux, Tesla for density. And laws. Does magnetism have laws like electricity?
It does, and they sound familiar. Law 1, repulsion attraction. Like poles repel. North repels north.
Yeah.
Unlike poles attract, north attracts south.
Just like charges?
Exactly. Law 2, the inverse square law applies again. The force between two magnetic poles decreases with the square of the distance between them.
Same as electric force.
Yep. And Law 3, magnetic poles. Every magnet has 2 poles, north and south. You can cut a magnet in half, but you just get 2 smaller magnets, each with a north and south pole. You always have a dipole.
No magnetic monopoles.
As far as we know, nope. Always dipoles. The parallels to electrostatics are striking.
What about magnetic induction? Is that like electrical induction?
Similar concept. It's making something magnetic temporarily by putting it in a magnetic field. The external field aligns the magnetic domains within the material.
So you can make a paperclip magnetic by rubbing it on a magnet.
Temporarily, yes. That's induction. How well a material does this depends on its properties, mainly permeability and retentivity.
Permeability.
How easily it can be magnetized. Retentivity is how well it stays magnetized after the external field is gone.
So different materials react differently.
Absolutely. We
Yep.
classify them ferromagnetic materials, iron, nickel, cobalt, highly permeable, easily magnetized, often high retentivity too. They make strong magnets. Paramagnetic materials, platinum, aluminum. Low permeability, weakly attracted to strong magnetic fields.
Weakly attracted.
Diamagnetic materials, beryllium, bismuth, lead. These are actually weakly repelled by magnetic fields. It's a subtle effect.
Repelled. Weird.
It is kind of weird. And finally, non-magnetic materials, wood, glass, rubber, plastic, they just don't interact with magnetic fields at all,
Sure.
unaffected.
Wood, glass, plastic. Got it. So this brings us back to the big picture. Electromagnetism.
The grand unification. The realization that electricity and magnetism are not separate forces. They are two facets of a single fundamental force, the electromagnetic force.
And Ørsted's experiment was key.
Crucial. He showed definitively that an electric current moving charges creates a magnetic field around it, and that field is perpendicular to the current.
Electricity makes magnetism.
That's the takeaway. It opened the door to understanding how these forces interact and how we can manipulate them.
Are there tools to help visualize this? Fleming's hand rules.
Yes, they're handy mnemonics. The right-hand thumb rule is great for a straight wire. Point your thumb in the direction of the current,
Okay.
and your fingers curl around the wire in the direction of the magnetic field lines. Helps you picture that perpendicular relationship.
Thumb for current, fingers for field. Simple.
Pretty useful.
This leads to things like solenoids, coils of wire.
Exactly. A solenoid is just a coil of wire. Run a current through it, and you get a magnetic field, much like a bar magnet's field, concentrated inside the coil.
And an electromagnet.
That's a solenoid with a ferromagnetic core, usually iron, placed inside. The core massively boosts the magnetic field strength.
Because the core material gets magnetized too.
Right. It enhances the field created by the coil.
Hmm.
The strength depends on things like the number of loops in the coil, the current strength, the core material's permeability, even the coil's size.
Where do we see these?
Oh, everywhere. Detent locks, holding components in X-ray tubes, giant scrapyard cranes, lifting cars, relays, circuit breakers. Very common.
So electricity creates magnetism. Can magnetism create electricity?
Ah, now you're talking about electromagnetic induction. Michael Faraday's huge discovery.
Faraday, right.
He showed that, yes, you can induce an electric current using magnetism, but there's a condition. You need motion.
Motion.
There has to be relative motion between a conductor and magnetic field lines. A changing magnetic environment for the conductor.
How can you get that motion?
Three main ways. One, move the conductor through a stationary magnetic field.
Okay. Wire moving past a magnet.
Two, move the magnetic field lines across the stationary conductor.
Magnet moving past a wire.
Yep. Or three, keep both stationary but change the strength of the magnetic field itself. A varying magnetic flux passing through the conductor loop.
So change is the key. A changing magnetic field induces current.
That's the heart of it. No change, no induced current.
And Faraday's law tells us how much current we get.
Faraday's law, yes, sometimes called the first law of electromagnetic induction. It says the strength of the induced current depends on four factors.
Okay, what are they?
One, the strength of the magnetic field. Stronger magnet, more current.
Makes sense.
Two, the speed of the relative motion. Faster movement, more current. Okay. Three, the angle between the conductor and the field lines. Cutting perpendicularly induces the most current. Parallel movement induces nothing.
Angle matters.
And four, the number of turns in the conducting coil. More turns means more wire interacting with the field, so more induced current.
Strength, speed, angle, turns. Got it. What about Lenz's law?
Lenz's law is like nature's conservation principle here. It says the induced current will always flow in a direction that creates a magnetic field opposing the change that caused it.
It fights back against the change.
In a way, yes. It ensures energy conservation. It's the second law of electromagnetics.
These principles, they must be behind a lot of our tech.
Absolutely fundamental. Think about generator.
Making electricity.
Right. They convert mechanical energy, spinning a turbine, say, into electrical energy. They use coils, rotating a magnetic field, exploiting electromagnetic induction. Things like slip rings help get the current out continuously.
And electric motors.
Basically, generators run in reverse. They take electrical energy and convert it into mechanical energy, into motion. Same principles, different energy conversion directions.
Motors are everywhere.
Blenders, fans, cars, pumps, and then transformers. Crucial devices.
They change voltage.
Exactly. They operate on mutual induction. You have two coils, primary and secondary, usually wrapped around an iron core.
Mutual induction.
Yeah, AC current in the primary coil creates a changing magnetic field in the core. That changing field then induces an AC current in the secondary coil.
And changing the number of turns changes the voltage.
Precisely. More turns on the secondary than the primary.
Right.
Step-up transformer increases voltage. Fewer turns. Step-down transformer decreases voltage. Essential for power distribution.
Wow. Okay, let's tie this all together with that X-ray circuit example you mentioned earlier. How does it all play out there?
It's a perfect showcase. You start with standard AC power from the wall, maybe 220 volts, 60 hertz.
Okay, standard house power.
That goes into the X-ray machine circuit. First stop, often a step-up transformer, a big one.
Using mutual induction to boost the voltage way up.
Way up. Tens or hundreds of thousands of volts are needed to generate X-rays effectively.
Then what? Still AC.
Good question. You need high voltage DC, direct current, to properly accelerate the electrons. So next come rectifiers.
Converting AC to DC.
Exactly. They act like one-way valves for current. This high voltage DC then powers the X-ray tube, heating a filament to release electrons, and then accelerating those electrons across the tube at incredible speeds using that huge potential difference.
And when those fast electrons smash into the target material?
Bang. X-rays are produced. But the efficiency of that whole process has improved massively. Early single-phase power had a lot of voltage ripple. The DC wasn't perfectly smooth, dropping to zero periodically. Not very efficient.
Right.
Three-phase power was better, less ripple. But modern high-frequency generators are the standard now. They use electronics to create very high-frequency AC before stepping up the voltage and rectifying it.
Resulting in?
Much smoother DC, very little ripple, maybe only 3 or 4%. That means more consistent electron acceleration and more efficient, controllable X-ray production. All thanks to applying these electromagnetic principles cleverly.
It really is amazing how it all connects. From the electron shells defining conductors, to Ohm's law in circuits, to moving charges creating magnetism, and that inducing current in generators and transformers, all ending up making an X-ray image.
It boils down to that moving electron, doesn't it? Its properties and interactions are behind atomic stability, the electricity in your walls via parallel circuits, the pull of a magnet, and these complex machines. It's pretty fundamental.
It really is. And hopefully understanding these core ideas gives you more than just facts. It gives you a deeper appreciation for, well, how the world works, all the unseen forces and intricate engineering around us.
Mm-hmm.
So here's something to think about. Now that you grasp how moving charge creates magnetism and how changing magnetism induces electricity, what other devices in your daily life, things we didn't even mention, might be quietly using electromagnetism in ways you hadn't considered?
Yeah, look around. Your wireless phone charger, induction cooktop, even tapping your credit card.
Lots to explore there. Definitely food for thought.